Let's take a look at an example where it's more beneficial to use our exponential growth formula, y equals a times b raised to the x. Again, we have two exponential growth formulas and they mean the same thing. It's just different situations that you want to use them in. The first one I showed you was y equals a times b raised to the x. And the second one that you were shown was we have c times 1 plus r raised to the t. They mean the same thing. Both a and c are initial values. This b and this 1 plus r both represent our growth rate, and x and t here both are our exponent, the number of times we're going to be raising our growth rate to. I said that this one here was beneficial when you're dealing with money and compound interest. If we look at this example, it says a population of 20 rabbits is released into a wildlife region. The population triples each year for 5 years. So in this case, since we're not talking about money, it's probably easier to use this first model. Again, they're the same thing, just each has their own pros when we're doing different types of problems. Okay, it says a population of 20 rabbits is released into a wildlife region. The population triples each year for 5 years. What is the population after 5 years? So if we use a times b raised to the x, our initial value, remember, is a. Our initial amount or our initial value. Well, our initial value is 20, so I'm going to substitute 20 in for a. Now, it triples each year. So b, remember, represents our growth factor, our growth rate. So it's tripling. So I'm going to say times 3. And now it wants to know our time. It's going to triple each year for 5 years. So we're going to put a 5 in for 3. I'm sorry, a 5 in for x. So if you type into your calculator 20 times 3 raised to the 5th, you get that your population, y, is going to be equal to 4,860. So we'll have 4,860 rabbits after 5 years. Now, that's great. It's the correct answer. But it doesn't really show how exponential growth works. So let's use this table down here so we can graph it. With linear functions, we can graph using slope-intercept form, and it's pretty easy. There are no shortcuts with exponential functions though. Yeah, there are some ideas of where it hits the y-axis and everything, but really you have to make an input-output table. So again, if we're going to use our formula here, y equals, and I'm going to leave it as 20 times 3, because that's the initial amount of rabbits, our growth rate, but I'm just going to raise it to the x. Oh, I'm sorry, they're actually using p and t down here. That's all right. We'll use x and y. So if we put a 0 in here for x, so if I go 20 times 3 raised to the 0, remember, anything raised to the 0 power is 1. So 20 times 1 equals 20. If I substitute a 1 in for x, I go 20 times 3 raised to the 1st. So 3 to the 1st is 3. Times 20 is going to be 60. And then you can just keep doing this. 20 times 3 to the 2nd is going to be 180. Remember, exponential growth, it tells us we're tripling it each time. Tripling 20 get 60. Tripling 60 get 180. Tripling 180, or 20 times 3 to the 3rd, you would come up with 540. Tripling 540, or 20 times 3 to the 4th. Again, we're just inputting numbers here for our x. We would come up with 1,620. And either tripling that again or plugging the numbers into our formula, you get 4,860, which I should have known because it was right here. With exponential growth, when you're asked to graph, it's really a good idea to probably do about 5 input-output values. Always going to want to include 0, because that's going to be where your initial value is. And you don't want to use really big ones, because really big input values, because your graph's going to take off. Okay, so let's look how we would graph this. Okay, and I'm actually going to jump over to a different slide here. Okay, so we wanted to, that's our input-output table we already created. We said after our initial value is 20, after 1 year we'd have 60 rabbits, 2 years 180, 3 years 540, and so on and so forth. And we knew after 5 years we'd have 4,860. Now let's watch the graph and what happens on the graph. If you were to graph these points, there's 0, 20, 160, 2, 180. Notice there's not much change right here. Okay, our graph, it almost looks like it could be linear. Not quite, but it almost does. That's why you shouldn't do 3 points. You got to keep going. There's 3, 540, 4, 16, 20, and then, oh my goodness, look what happens. As slow as we're going, all of a sudden our graph takes off. And that's what people mean when they say it's exponential growth or that grows exponentially. It doesn't change a lot at the beginning, but the more you stick with it and the more it keeps going, like it says here, the large growth factor of 3 corresponds to a rapid increase. It doesn't seem very rapid at the beginning, but then it's going to take off, and it's going to keep taking off because remember, we're tripling these values every single time. So exponential growth starts small and then explodes the more it goes. And to graph a function in exponential growth, you do need to make an input-output table. Always beneficial to start with 0, even maybe just go 0 through 5. On the negative side, it's just going to, remember, it's never going to cross the x-axis. It's just going to keep getting smaller and smaller. So graphing exponential functions, input-output table, plot your points, and then try to draw a smooth curve through them.